Welcome back to Math 104. We begin our fourth set of videos on probability. Last time we were discussing the birthday problem. For example, we worked out how to answer the following question. If there are 23 people in a room, what is the probability that they all have different birthdays? And then what is the probability that they don't all have different birthdays? That is, at least two people among them have the same birthday. That is, that there is a shared birthday among them. These are different ways of describing the complementary event to the event that they all have different birthdays. We relied heavily on the multiplication principle of counting to work out the probability that all 23 people have different birthdays. We have to count up in the numerator all the outcomes in the event that they all have different birthdays, and we have to count up in the denominator all the different possible outcomes in the experiment of asking 23 people what their birthdays are. In both numerator and denominator, there are 23 numbers being multiplied together because the experiment of asking everyone their birthday is a 23-stage experiment. You ask person number 1, what's your birthday? You ask person number 2, what's your birthday? So there are 23 slots here, each one filled by a particular number. In the denominator, each slot is filled by 365 because we're counting the total possibilities for the experiment. And in the numerator, that's where the number of possibilities decreases for each subsequent person. Having computed that the probability of all distinct birthdays is slightly less than 0.5, it follows that the complementary probability of not all distinct birthdays is slightly greater than 0.5. What's the conclusion? The conclusion is that when a common birthday, a shared birthday, is discovered somewhere among 23 people, it is not a remarkable coincidence. On the contrary, it is more likely to occur than not to occur just by chance. In the same spirit, let's look at some more examples of coincidences that are actually not so remarkable. In other words, things that actually can perfectly well occur by chance, and just by chance, that you might not have thought of as happening just by chance. To do this, let's return to our favorite type of experiment, the kind of experiments whose outcomes can be represented as words in an alphabet with just 2 letters. That means that the experiment has a certain number of stages, that's the number of letters in the word, and at each stage, there are only 2 possibilities for what can happen. As an example, suppose that 2 equally matched baseball teams meet in the World Series. Let us call them the Yankees, represented by the letter Y, and the Mets, represented by the letter M. We're just going to imagine that these are equally matched teams. The way the World Series works is that the first team to win 4 games is the winner of the series. That means that the winning team could win 4 games to none, then the series lasts only 4 games, or 4 games to 1, in which case the series lasts 5 games, or it could last 6 games, or it could last 7 games. It could be that one team wins 4 games and the other team wins 3, but it could not last any more than 7 games. Let's focus on a series which lasts just 4 games, the bare minimum, which means that one team wins the first 4 games and that's it. The series ends as quickly as possible. This is called a sweep. Now we can ask, what is the probability of a sweep, assuming that the teams really are equally matched? Let's first think, how can we represent the outcomes? Now remember that we're just focusing on the first 4 games. We will find out just by looking at the first 4 games whether a sweep occurs or not. Either one team wins those first 4 games, in which case we have a sweep, or it is not the case that one team wins all 4 of those first 4 games, in which case we don't have a sweep. So this experiment of seeing whether a sweep occurs or not depends just on looking at the first 4 games. Therefore, we can represent the outcomes just as 4-letter words consisting of Y's and M's. This means that there are a total of 2 times 2 times 2 times 2 different possible outcomes. That's because there are 4 stages of this experiment and 2 possible results at each stage. In particular, there are 16 different 4-letter words consisting of Y's and M's. We can ask, of these 16 words, which ones correspond to a sweep? There are 2 different words, Y, or MMMM. Either team could be the one that carries out the sweep, so there are actually two outcomes in our event. There are 16 equally likely outcomes in the sample space, therefore the probability of a sweep equals 2 out of 16, or 1 out of 8, which equals 0.125. There is a 12.5% chance that a sweep occurs, even though the teams really are equally matched. Now here we made an assumption about the teams being equally matched. What if you don't know whether they're equally matched or not? You just watch the World Series and a sweep occurs. Well, if a sweep does occur, there's a question. How convinced are you that the winning team is dramatically better than the losing team? You might think that if one team wins 4 games and the other team can't win any, that the winning team must be much better than the losing team. When a sweep does occur, it is evidence that one team is much better than the other, but it's also possible that it happened just by chance. For our next example, suppose that a true-false exam with 10 questions is randomly generated. That means that all possible answer keys are equally likely. All possible sequences of the correct answers are equally likely. The correct answers might be all true, they might be all false, they might be 6 true and 4 false jumbled up in some order. All the various possibilities for what the sequence of correct answers could be are equally likely. Before going on to the next video, find the answer to the following question. What is the probability that the correct answers to the first 4 questions on the test are either all true or all false?